Hello and welcome. This is section 4, chapter 1, physics 313, and another relatively short video with a central important concept, and that's velocity. In the previous videos, like I said, we have been developing the idea of a motion diagram by starting off with an image moving from point to point, overlaying that sequence of images with a coordinate system. And from that coordinate system with its origin and its direction of positivity, now we have a vector that describes its position for different instances in time. We've also defined a time interval, and the difference between positions at the time interval is defined to be displacement. So displacement is a central topic from when and it's our first really physical quantity that we define, in addition to time interval being the second. So we combine those two to give velocity. But before we formally define that, we have kind of a half step to define average speed. Average speed is defined as the distance traveled by an object over the total time interval. Now, chapter 3 has a formal definition of this, but technically distance traveled is a scalar. Technically, time interval is a scalar and average speed are scalars. That means that they're just numbers. There's no direction associated with them. There's no direction with saying you traveled 10 miles to go from here to the other side of town. Okay, same thing with average speed and time interval. There's technically an arrow of time, but it's always assumed that time is going from past to the future. So there's no vector associated with that either. And so that makes all of these scalar quantities. And so the information that you miss out on is the direction. And so we actually define what we call average velocity. We define average velocity as the displacement between two positions divided by the time interval. So this average velocity, it's a statement. By saying average, it's assuming that the object can speed up or slow down during the course of that time interval, but it's just the final position minus the initial position. So you go on vacation or you start a long trip driving, right? Let's say it takes you 6 hours to get from here to the nearest city. Obviously, in that time, say if the city's like 300 miles away. Obviously you start the car, you speed up to get to the final traveling speed. You might stop to take a rest. You might speed up back again. You might increase speed to 70 or decrease to 60 or 55. Maybe there's construction, so you go down to 40 miles per hour. All these little fluctuations in what we would call instantaneous velocity and instantaneous speed, those get fluctuated out, and the average is only just the final minus the initial. All that we care about is that it took you 6 hours to go 300 miles. Doesn't matter how much you traveled during that time, or increase or decreases in speed. And so, considering the vector nature of this, displacement and velocity are two vectors that are directly proportional to one another. And this is kind of an underlying idea about vectors in general, is that you can multiply them by scalars. You can multiply them by real numbers. And what that's going to do, that's going to preserve the direction, it's going to preserve the orientation of the vector, but it'll stretch it or squish it depending on if the object is, greater than or less than or 1 respectively. And typically what that means is that the time interval is very slow. And so you'll have a very tiny displacement divided by a very tiny time interval. And that'll usually make a reasonable size velocity vector. And so now to add to these motion diagrams, we're connecting the dots. Technically, the arrow between these dots on a motion diagram is a displacement vector, but we're going to say that this displacement vector is scaled proportionally to the correct time interval. And so that means that these arrows will now represent velocity, average velocity. And so this is the next step in creating our motion diagrams, that we will have our, in addition to our dots representing the positions at specific time stamps. In addition to our coordinate systems, now we have arrows connecting the dots representing velocity, average velocity in that time interval. And we are almost done. And in fact, for a type of motion where the speed is constant, this technically is a complete motion diagram. And so here's a nice example, actually in the textbook, of accelerating up a hill. You can see that the vectors get, the velocity vectors get larger as time goes on. And so in addition to that, the positions are getting further and further apart in those equal time intervals. So what does that mean? That means that there's something that is describing how the velocity itself changes, right? Because the velocity vector, going back to the previous slide, the velocity vector shows how the position changes, right? Those dots, the fact that those dots are moving is represented by these velocity vectors. But there's got to be a vector that describes how the velocity vectors themselves are changing. And that is actually the topic of the next video on acceleration. So this concludes the video on section 1.4 velocity. In the next video, we'll continue and complete our discussion with linear acceleration. As always, thanks for watching.